All right. I've just been having problems with today with the Wi-Fi. Okay. No, we were not there. We were here. Yeah, let's go here. I just so let me see. Put my. All right. First of all, Friday we don't have a class, so you know. I'm sure you know, but I think I am for sure. You know, I know that we don't. What we don't know is when the class is. When we have a class, that's what we don't know. When we don't have a class, that's okay. That's part of life. I've been there, I've done that, as they say. Yeah. Okay. All right. So I wanted to, can you hear me, everyone? So modules, I wanted to go to the last module. And we had a top hat exercise in class, 502. I think I like those now. I will do them because I can see, you know, just on the theory to put it on specific things we've discussed. I had a top hat in class in the morning, but because very few people were there anyways, and very few people did well, I put the solution and I'm going to give them another opportunity for another top hat. The solution is there. And what I plan to do is to put all of the solutions for exercises by week. So you will see them as you prepare eventually in the next 3 weeks for the final. So what I wanted to do is to use that as an example, all right? Because now you can see here we have, when you look at what it says, important equations, use that and use this document to augment, to put any other equations or something similar to that, that you would like to have available, all right? For the solutions of the problems and so forth. Okay, that is nothing, it was a leftover. So what I would like to do today is to use these equations and then solve problems. All right, so we'll do the following. I'm gonna go to, first of all, the first problem then we would like to do. There are two important problems I would like to do. That you, hopefully you're gonna keep them in mind. And we did the open end and the short end last time, isn't it? The open ended and then, okay, we got that. So now, another important problem is, which you need to remember, right? So you don't have to, here I derive it, but my suggestion is remember it. Is what happens, now that we've seen what happens when the line is matched, all right? We saw matched line, and what happens when the line is matched, like the load is equal to the characteristic impedance, what happens to the reflection coefficient is 0. Okay, perfect. What happens to the reflection coefficient when the line, to the magnitude of the reflection coefficient when the line is open? How much is the magnitude of the reflection coefficient when the line is open? This is what we've done last time. Let me hear. No, the other one. What happened to the magnitude of the reflection coefficient? These two equations tell you the story. What do they tell you? One is at the node, at the load. Gamma sub L is 1, which means that you have magnitude of 1 and what phase? Remember the circle? Where should the phase be so you have 1 as a magnitude? 0 to pi. 4 pi. I mean, we are from 0 to 2 pi, all right? We don't go beyond that, obviously. So 0 is the phase here, okay? But I'm talking about the magnitude right now, because the magnitude of the reflection coefficient at the end is equal to the magnitude of the reflection coefficient where? Everywhere on the line. You remember that? Or the magnitude of the reflection coefficient everywhere on the line is equal to the magnitude of the reflection coefficient at the end. Remember that? Very important. This one. Well, the one that we had, well, in this case, because it's 1, you see 1, but we have learned a general formulation for the reflection coefficient, which is here. You see that? D is the distance from the load. L is the length of the line. Remember, whenever I show L, L is for length of the line, total. D is for distance from the load. Okay, remember this. So, if I am at the point Z, which is at the distance D from the load, all right, what do I see here? The only change that I have from what the reflection coefficient is here, if I'm here, which is at the distance D from the load, the only change between this reflection coefficient and this one is in the phase. All right, don't forget that. Okay, so on the basis of this, now we go to the open, and we saw that the magnitude in the open is 1. And then, of course, whatever comes then after I move away from the open is going to give me phase change. All right. This is true for every load. In every case, for the reflection coefficient, as I move from the load towards the source, the only thing that I get as a change is in the phase, not in the magnitude. All right, that's number 1. Then, so we did the open circuit. Also, you need to remember that for the open circuit, the input impedance everywhere on the line is given in this form, where D is my distance from the load. All right. And when it's short, and we call it also a shorted stub. Remember, I told you last time when it's shorted the line and it has a particular length, we call it stub. We're going to use them next week. When it's open, we call it an open circuited stub. All right. And therefore, when it's shorted, the input impedance is like this. All right. And it takes this form. Okay. Now, we had maxed, open, and short, important. Now we have a third case, which I have, I'm putting it separately so you see from the title, you don't get confused. Lines terminated in reactive loads. What is a reactive load? An inductor or a capacitor. And I have it here as a JX to indicate both an inductor and a capacitor. If this is an inductor, what is X? Omega L. Omega L. If J, which, so you're correct. If Isabel is a capacitor, what is X? Minus 1 over omega C. So negative for capacitor, positive for inductor, but they are reactive loads. Let's see what happens if the load is reactive, regardless of whether it's positive or negative. Very interesting stuff. Gamma L, always, we start with gamma L, because the moment I find gamma L, then I can find gamma everywhere on the line, the reflection coefficient. Reflection coefficient, therefore, at the end is the load minus the characteristic impedance divided by the load plus the characteristic impedance, all right? Always formula, you remember. So now, load, I put it Jx minus Z naught over Jx plus Z naught. Immediately, how much is the magnitude of this? 1. Yes, thank you. The magnitude of this is 1. We can prove it, but you need to remember, if you have the ratio if you have the ratio of a complex number divided by its complex conjugate, the magnitude is 1, period. All right? Okay, but of course there is a phase. How much is the phase of this? The phase of the numerator is minus the phase of the denominator, because there is a minus sign. Otherwise, this will be the same. All right. So the phase is here the negative of the inverse tangent of x minus over z naught. Okay. Yes. No. Yes. And that is the negative of this phase. So I can write this as 1, and the phase for this is going to be the phase of the numerator minus the phase of the denominator. The phase of the numerator is f1, which is minus f2. So if I can substitute f1 for minus f2, I have 2 minus f2 here. All right, so the phase at the load is minus 2 f2. How much is f2? F2 is x, is the inverse tangent of x over z naught. Therefore, is this number. Okay. So there are 2 possibilities for this. This can be positive if it's done. As we said, you remember we said x is positive if it's an inductor. And therefore, this is going to be positive. If this is a capacitor, this is going to be negative. Okay? So, if this one is 90 degrees, which is pi over 2, then this one, according to the relationship here, if phi sub L is 90 degrees, this one is 45. All right, so the inverse tangent of x over z naught is pi over 4. And therefore, is, according to the tangent, is down here. And the tangent over x over the inverse tangent of this is pi over 4. And therefore, to be here, tangent therefore of pi over 4 is here, which means that x over z naught is positive. So, in other words, if, so this is an example, but if the inverse tangent of this is, excuse me, if this is positive, which means inductive, then the inverse tangent of this, especially if it's below pi over 2, because from this. So here you can see there are 2 regions where the tangent, which is x over z naught, can be positive. If the angle is less than pi over 2, or if it's too large. But here, we are below pi over 2 according to this problem. So that's what you find about the inductive. Therefore, if x is inductive, there are only these 2 regions where your phase can be in deflection coefficient, right? Or the reverse. If I give you the phase of the reflection coefficient, then you can find in whether your load is inductive or capacitive. But inductive up here, capacitive down there, all right? Usually we work in less than pi. So you we're gonna be in this. So inductive here, capacitor, all right? So look at this problem, because what I would like you to do, and that's gonna take time. That's why we do all of these examples. I don't want you to get lost into the math. I want you to start getting a feel without having to worry about the math all the time. We're gonna solve a number of problems, especially, when you're gonna clarify all of this in your mind when we go to the Smith chart, because then it's gonna be visual. You're gonna see all of this in a very visual way. But this is a problem, and in this problem, somehow they tell us information about gamma sub L because somehow they measured it. They found this. They measured here, they transferred it there, and then they found how much was the reflection coefficient at this point. And from that, you can get information about your load, which is true, all right, because of this relationship. You don't know it in the beginning, but because you have information about this, that is one, and then they give you information about the phase, you go and find X. All right, I could give you other information, I could give you another number about the phase, and you would find exactly the value for X. Do you understand that process? The solution? Yes? No? Okay. Now, we are going to solve some other problems. We are going to start slowly then, asking the following. I will summarize it here. And that will be, we'll start asking design questions. What is a design question? So far, what we've done is analysis, which means that I have, instead of redrawing it, I will copy this. Copy. Paste. Okay. So now, let's assume that we have a general load. All right. So far, everything is given to us. This one, C naught, C sub L, beta, or F or lambda. Beta means, when I say beta is given, what do I mean? That either the frequency is given or lambda. All right. Because if I give you frequency from the product, F times frequency, F times lambda equals C, which is the velocity of light in free space, since we use free space here. From that, if I give you F, you know lambda. And if you lambda, how do you know beta? What is beta in terms of lambda? 2 pi over lambda. Don't forget that. Beta is 2 pi over lambda. What is omega? Radial frequency. 2 pi times frequency. Omega is 2 pi f, all right? And beta is 2 pi over lambda. Remember those two. Very important. These are the most fundamental things. Omega is 2 pi f. Beta is 2 pi over lambda. And f times lambda equals c. If you could only keep in your brain, which I don't think it's only that, you can keep many more things, but if you can only keep 3 things, it will be these 3, if I have to choose. These are how fundamental those are. And then everything else. Okay, so if I give you F, I only need to give you F and Z naught, or if I give you beta, then you know lambda, you know what, and Z naught. And of course, if I give you this, so these two, Z naught and beta, define the line. These 2 parameters, Z naught and beta, define the line. And of course, it's length from that third parameter. So these two define the line as an infinite line. These two, this one is telling us that it's finite. There's a length there. This is the load. If I give you the load, the line characteristics, and this sub S, Then I can ask you a lot of things about what happens inside the line. I can ask you about the inflection coefficient here. First of all, I can ask about the inflection coefficient at any point. I can ask you about the characteristic impedance at any point. These are all called analysis problems. Now, what I can do in retrospect is the following: to say, I have a line that has a given length L, and I have a load. In fact, I have a load, Isabel. I have a line, but I can modify its length, for example, at a minimum. And then I have a source. Maybe I can tell you in a different way. I have an antenna, all right? I represent the antenna with a Isabel. And then I have a source. I can excite the antenna. And then I have a cable. And I can choose how long to make the cable. I can choose a lot of things, but this is the cable. I have a particular cable. Then what I would like to do is to move most of the real power from the source to my antenna. And the question is, what length should I choose? Number one. And is that enough to give me the maximum power from the source to transfer it to the antenna? That's a design problem, all right? Because I'm giving you a particular, I'm asking you to design a line, but I'm telling you what kind of cable I have. In other words, I'm telling you what is Z naught. I'm telling you what is beta. And then I only allow you to change L to decide how long of a cable you're going to use from my source to the antenna, so this antenna can radiate the maximum power. Now, in a problem like this, where this is a complex number, all right, has a real and imaginary part, and where to be able to move the maximum real value of the power, the maximum real power from the source to the load, which means that I need to have a particular matching condition here. All right, I need practically to make sure, in this particular case where I don't have an internal impedance, when I say that I want to take all of this power from here and move it there, what does it mean? That I need to have a reflection coefficient 0 at this point. All right, I need to make, and if I had an input impedance ZS, let's do that because that is even more complete of a problem. So I could say, okay, I can have an impedance here ZS, and then I can have my source. And now I know, however, if I know my source, I know ZS, all right? The source is part of the source. So now I'm saying this is, now I'm more realistic. I say now I want the real power that is produced by that, all of it, or the maximum of it, as much as possible physically. I want to move it from here to this. That's a design problem. Which means that I need at this point to have an input impedance that does what? What did we say last time? According to the conjugate matching, how much should it be the impedance that I see here? Conjugate matching. What did we say last time by conjugate matching? What is conjugate matching? Come on, guys. We talked about it. Who remembers circuits? The word says it. If you cannot think about it, it says, why do I call it conjugate matching? Conjugate, what conjugate means? That something, if I have a complex, the other has to be the complex conjugate. Conjugate means that, all right? Complex here, when I mean conjugate, the other, whatever I have to match, it has to be the complex conjugate. What do I have to match here? This to that. Remember from circuits? When I have a source with a complex load, to move the maximum real power from the source to my, with a complex internal impedance rather, to move my, the maximum real power from this sub S to the load, my load has to be the complex conjugate of that. Do you remember that? Yes, no? Okay, if it's like that, it has to be, yes, it has to move from this to yes, which means that you guys have to go and remember that, all right? But if we have, I will do it only once more rather. So practically, if I have here, copy. If I have this one here from circuits, the equivalent to this on the front end is like having an impedance here, Z input, A prime. All right, so this one is a circuit representation of this part, the front part of the transmission line. Why is this important? The input AA prime, because I can replace at that point the whole line with this impedance. All right, the whole line. That's why it is useful to find it. Because if I know that, then practically everything here is simplified to this. And now I can say, how can I get the maximum power from this to that by making it a complex conjugate? That's what I know from circuits. So for maximum power, to Z input at AA prime, which now represents the whole line, I need to make Z input at AA prime the complex conjugate of Z sub S. That's the condition, all right? So now that I know that I have to match this load that is separated by this line from the source, I have somehow to find L to see if I choose an L only, like a length, can I match this to the source? Okay. Now, what happens if the source has only a real internal impedance, Z naught? What is going to happen to this one? How much is this going to be? Z naught. It's going to be, I mean, if this is real, this is real. So, but in any case, the moment we know that and we know it from the source, then you know how much this should be. All right. But then the question is, can I only change the length of the line to match this to that? And the answer is not all the time, only in special cases. As a matter of fact, for a general load here, we need more than just the length of the line to control. All right. Okay, so we'll see now specific cases. We'll call, first of all, we see what we call the quarter wavelength transformer. Okay, so when does this happen? We are now going into the design space, all right? Everything we did before, it was the analysis space. When we write all of the equations, we try to get a feel. You know, when you analyze the problem, what do you try to do? And this is in general in engineering. When you guys go to do your capstone design and you get a you choose to do a problem. What do you try to do first of all, before you go to the lab and try to put things together? You try to understand what we call your design space. What does that mean? You try to understand all of the relationships between the performance of your circuit and your geometries and your components or whatever else you have and your architecture. So when you try to understand how your circuit performs for different types of variables, that is called analysis, all right? Because you do analyze it. You don't design anything. You try to understand, how does my load relate to reflection? How does my length relate to the reflection? How my length relates to what I see at the input? I mean, all of these questions that we have seen. What happens if this is open to my reflection coefficient? What happens when this is reactive to my reflection coefficient? All of these questions are helping you understand your design space, where you're gonna make your trade-offs. All right, what are the relationships? Which things will be doable and which things are not doable, or what parameters control what? All of this is the beginning of your project. If you don't do that, there is no end to the project. You're not going to be successful in doing anything at the end. So this is the first thing. Then you move to the design process. Well, then after you've understood everything from the analysis, whatever the analysis will give you, now you try to specify things here. That is called the design phase. All right. So everything we did before was the analysis phase. So now we go to design. And for us, for the design phase, we are going to learn some tricks. All right. Never in design you start from scratch, because then it will never end. So you try to learn from other people's designs, all right, and use those, or at least modify them a little bit, or use combine. I mean, I need to know what you've done and you were successful, and what you've done and you were successful, and then I maybe try to put them together, modify them a little bit, do whatever I have to do for my problem. All right, that's how design goes. So in the design phase, we're gonna learn some designs that other people applied, which were successful. Okay, so first of all is the quarter wavelength transformer, very famous quarter wave transformer. Okay, so in this particular design, somebody found a nice way to match a real load to a source. So the problem is the following. We have the same two designs in two different contexts. One is to connect a source with an internal impedance of Z0 here, okay, BS. And now I have a load which is real. Let's assume that the load is an antenna at resonance. Usually antennas that operate at the resonant frequency have real impedances. So it's a real load. So I'll put here R sub L. Okay, and now I wanna find, and I wanna connect my source to my antenna, which is far away. No, far away could be from here to the end of the room. If it is low frequency, could be from here to here, if it is high frequency, right? So I'll put a transmission line in between because we're talking about high frequencies. Okay, so I'm gonna tell you exactly what the first designer who applied that did, and then we can prove it. But I will tell you the first designer who did that, he knew rather, not women at that time, that this input impedance here at A prime has to be equal to Z naught. Remember we said that? The result of conjugate matching, since Z naught is real, the input impedance has to be there to be equal to Z naught. And then if that happens, all of the maximum of the real power here is delivered to the antenna if we do the good design. Then he found that if I keep the length of this, if I have the length of this to be a quarter of a wavelength, or an integer, or a integer multiplier of a quarter of a wavelength, then, but usually we don't go to long lines, so we try to find the shortest possible, electrically speaking, line to do the matching, all right? We don't want to add lengths and lengths of line, because if you do that, then your design becomes very big, physically speaking. Okay, so the shortest that this person could find was lambda over 4. And then this person realized that I need also to change this characteristic impedance. It cannot be Z1. So quarter of a wavelength, the moment you make that a quarter of a wavelength, this person found that if Z1 is the square root of R sub L and Z naught, then a quarter wavelength line of this Z1 will make this load appear at this moment, at this point, like Z naught. All right, that's called the quarter wavelength transformer, because it transforms this load, which is R sub L, to Z naught. All right, very important. Okay, and this is called a quarter wave transformer, because it's a quarter of a wave transforms the load to Z naught. And the basic formula for that, the characteristic impedance of this new line, has to be given by this formula. In the homework you're going to give you, I will ask you to prove it. All right, I will ask you to prove that if I put a load here, any load R sub L, real, and if I put a quarter of a wavelength line, then this characteristic impedance can transfer this load and make it Z naught here. How are you going to do this? You're going to use the property, the formula for the input impedance here of this line connected to RL, and you will find Z naught. Okay? All right, so that is the quarter wavelength transformer. So that's the most important, one of the most important ways of matching, because that's what you've done. You match your real load to Z naught, real. Okay, now, what if our load is not real? Then I will describe these two. So you have non, or rather you have complex loads. Complex loads. What is a complex load? Complex load is a resistor in parallel with an inductor, or a resistor in shunt or in parallel with a capacitor, or anything that has a reactive element. A resistor plus a reactive element. I mean, in some kind of arrangement, all right? So whether it is in shunt with a capacitor, whether it is in series with a capacitor, whether it is in series with the inductor, all of that depends on whatever the load is. The load obviously is not going to be like something, it's going to be another component. All right, the load can be an antenna that performs away from resonance. When an antenna, the dipole antenna, performs below resonance, is capacitive. When it goes above resonance, is inductive. All right, and then at resonance is resistive. So it has a resistance in series with a capacitance before, a resistance in series with an inductance above resonance. So it can change. It could be another, it could be an active, it could be a low noise amplifier that has a real and imaginary part. And whether it is capacitive or inductive, the imaginary part that comes from the load is going to depend on how it operates. Okay, so complex loads. In that case, let's assume that I have a transmission line here. The load, let's assume that the load for a second is a resistor. And then in parallel with an inductance. And then I have a transmission line. I need to move from the load to the transmission line. All right. I will rewrite this a little more clearly. And let's assume now that somebody tells you, find me this transmission line, and you have the freedom to either specify its length or specify its Z0 or specify both, but do it in a way. So when I connect this to a source, when I connect this to a source, I get the maximum real power out of the source. All right? And let's assume that this is Z0, just to make things simpler, real. So again, in this case, while I have an RL, an L, an R and L for the load, which means my load Isabel is going to be R plus J omega L, all right? Then, let me do that, I don't have to do it. Okay, so then in that case, I will have to find this distance D, lambda L, excuse me, L. And maybe if I knew only the previous, let's assume that I know only the quarter wavelength transformer, say, can I do a quarter wavelength transformer? So you try it, but then you see you can't, because in the quarter wavelength transformer, Z1, all of the characteristic impedances have to be real. So it's only a real load that will give you a real characteristic impedance here. So if it were to be real, yes, but now it's not real. So it is real plus an inductor. So now I'm starting thinking, okay, what am I gonna do? Well, how can you cancel an inductor? One frequency, not too many. How, if I have an inductor, how can I cancel an inductor? Yes, put a capacitor in series. All right, I have other problems. I have the problem that they will resonate somewhere, all right? But I want this resonance because they will cancel out. It's a series resonance, all right? So I can put here a capacitor. And I can put the capacitor in such a way, let me see. So now my load, the new load, is gonna become ZL I'll put it all with red. So you know it's because of the capacitor. Z L nu is gonna be R plus J omega L plus 1 over J omega C. And this one here, I can cancel all of the imaginary part. And as a matter of fact, I can write it like this so you can recognize it from circuit theory. And here is 1 minus 1 over omega squared LC. So at one frequency, at omega naught, which is called the design frequency, where omega 0 squared LC equals 1, which means that omega naught is 1 over square root of LC, that you have seen this kind of resonant frequency. At that particular frequency, how much is my load? At that frequency, my load is going to be R sub L, R. Okay, do you agree? At omega equals omega naught. So that's a thought. That's what I would think if I did not know anything else. All right, I'll say I'll put a capacitor. And then I'm going to make L equal a quarter of a wavelength. So then I make that equals to lambda naught over 4 at that frequency. And then I will make Z1 here to be the square root between R and Z naught. Now, this is a design. At one, I can make it work at one frequency. That's fine. There is no design that is going to work at all frequencies. Like, how do I call that? So it's going to have a bandwidth, all right? It's not going to be from 0 to infinite. The same. All designs are around a particular frequency. This is a particular frequency, and it's called the design frequency. It's called the design frequency because at that frequency I make it work. Now, what we're going to learn, while on paper this is correct, what we are going to learn on Monday is that instead of using lumped elements, because I don't, that's the other thing. They tell you your frequency is so high, you cannot use lumped elements. I don't have this capacity. They're so tiny, where are you going to put it? So, but you say you can use a section of a line to create that. So we are going to use a section of a line to create a capacitor. And the line is going to be either short or open. That's why we call them stubs. And we're going to select the one that gives the shortest length. And that is going to be a design, all right? So that's how we like to go about doing designs in circuits like this. Okay, I will open up an exercise for you. Let me see. So you will have to do it by Monday, and I will give you also homework on Sunday. But by Monday morning, when we come back, going here. Okay. Okay, let me see. All right, so I will ask you to do, you have seen you have seen already 13B, but I would like you to do both 13A and 13B. All right. And I will open both of them. I would like to see how many students they will be able to read the solution that I gave for 13B. Well, somebody is so much anxious to do it that making a mistake. Who is the person? Oh my goodness. Okay, I don't want to see that. Don't look at this because you're going to make mistakes too. One of them is wrong. Oh, I'm sorry. But I have the solution. I don't care. The solution is there, as a matter of fact. But now you can see that these people. So I was thinking, what do? They go like in a play roulette. You throw like that. That's it, isn't it? My God, but that's Russian roulette. If you play it, you're gonna hit yourself at the end with all of the points you're gonna lose. Okay. Yeah, they close their eyes and then they throw the dart, whatever. Jesus. I mean, I don't know. I was not that risk taker. Well, I was more careful than that. I mean, I'm not saying that I was doing better stuff, but when I was in your age, I did my own share. Okay, so you're gonna do this, and then we're gonna have homework. All right, so enjoy.
You're still sharing your screen.
Huh? Oh, I'm sorry. I'm reading about my granddaughter.
Question. So, first thing is, I was in my grades. I realized that one of my homeworks was not graded. One of my individual homeworks.
When was that?
It was number 4, I think.
Did I not? I sent you email, isn't it?
I didn't email. I submitted it, but it was late. But it was one time when I was in office hours, and they said you can submit it before the instant release. So I submitted it around like 9.
Is it still now?
Yeah,
Okay.
it's not
I will send that. So send me a note with your name.
Yeah. Okay.
So they can go and grade it.
So the thing is, would it be possible that to get some points back for like a team assignment if we think we did it right?
Mhm.
Okay, because I think one of our assignments was graded really low.
Okay.
But we think we did the right answer.
Then your team assignment, then you discuss it with me.
Okay, yeah. So
Why do you not in your email? Send me an email.
I just want to I was trying to ask you if it was possible.
Of course.
I'll find it. So I sent you a follow-up email about the group that I was leading and where I would go.
You send me an email through Canvas or?
Oh, just standard.
I did not, to tell you the truth, I did not see this email. When did you send it to me?
I sent it right before class.
Before this class. That's why I did not see it. All right. Okay, sounds good. I will make the change.
Perfect. Thanks so much.
Sure.
Have a nice weekend.
Bye-bye, you too.